Hello everyone. I'm grateful that to present my research journal about enhanced matrix-based error correction coding techniques for embedded memories. Now, coming to the introduction, in today's digital world, we all know that memories play an important role in storing of data. The data which is stored in these memories are used for further computation in the further functioning of the operation of the systems. And there are nowadays semiconductor memories like ROM and static random access memory and dynamic random access memories are used for storage of data. And these memories use different types of storage for storing single bit data and multi-bit data. So if we see that there are memories, these memories play a vital role in this computation world. So what is the motivation behind this work? See, most commonly, the memories are part of computation system as well as a communication architecture, which are part of action. Generally, these are aligned towards the errors, experiencing errors due to different types of noise sources, such as electromagnetic interfaces or power supply noise or thermal noise or short noise. And due to the complex structure of this architecture of these memories, they are aligned towards radiation-induced errors like single bit upset and multi-bit upset. To reduce those errors, that's the to reduce those errors and give an output without any errors is the motivation behind this. Coming to the objective, to design and implement an enhanced matrix based error correction coding technique with correction masking technique for memories. This is the main objective of our research paper. Coming to syndrome-based decoder with correction masking technique. So let me brief you about the syndrome-based decoder. How does it work? Syndrome-based decoder is generally an decoder which is used to detect and correct the errors which the from the input it is given. So how does this work? The major thing in the syndrome based vector is two things: parity check matrix and a syndrome vector. Parity check matrix is used to create parity check equations, which will be used to compute the syndrome vector. So the syndrome vector is the major thing over here. So and the other technique which we are implementing with this syndrome-based decoder is correction masking technique. So what's the use of this correction masking technique and why are we are implementing with this syndrome-based decoder? So coming to the correction masking technique is an existing effective way in which the error pattern is created with the help of the syndrome vector, which I'll be discussing in further presentation. So in that, the error patterns sometimes get corrected due to some different reasons, like which I have mentioned previously. So to not correct the error bits, we used to mask the error bits using a kind of method called correction masking technique. This is the use of the correction masking technique. So let me dive into how this syndrome-based decoder with correction masking technique works. So the first thing is that the computation of the syndrome vector. Syndrome vector, how does the syndrome vector, we will be computing the syndrome vector. So there will be a received vector which will be coming from the memory. Either it contains error or not, we'll further know it. So first, the syndrome for the received vector, which is received at the decoder, is multiplied with the parity check equations, which are generated from the parity check matrix or a H matrix. Then it produces a syndrome vector called SK. So when the SK syndrome vector is produced, we generally see that if the syndrome vector is zero, I mean all the bits in the syndrome vectors are zero, then we can say that the input data which is given to the decoder is error free. There is no error in the input. If there is any one non-zero bit in the data, we can say that the input data which is given to the decoder consists of an error. And one more thing is that the equations, the parity check equations which we are using to find the syndrome vector are individual and shares no logic in them. No logic is shared between the equations. Once the syndrome vector is produced, then all the bits in the syndrome vector is odd and variable called correction en is used. So why do we produce this correction en? This correction en is XORed with ANDed with EK, which is an error pattern. How does we like? Let us discuss how does this error patterns are produced. So if we get a non-zero syndrome vector, then the syndrome vector is compared with the columns of the H matrix, like the parity check matrix, and this is done to find the location of the error in the input data. If there are more than two errors present in the input data, then the columns, like the position of both the will be XORed. So, XORed, and the syndrome, the final error patterns will be produced at that positions. So after the error patterns is produced, then the EK, like the error pattern is denoted by EK, and this correction EN, both are ANDed. So at this point of time, the correction masking technique comes into play. Whatever the EK is ANDed with correction EN, this is where the correctable, non-correctable correct bits are masked and the error bits are not masked. So by this, only the error bits which are in the position are changed during the final output. At the final output, we will XOR the input data, the input data of the decoder with this EK into EK ANDed with correction EM. So the output of this, which we have denoted with DK correction, will be an error field, like the errors which we have, which has been in the input data will be corrected. Then, so as we discussed in the previous slide, we will use an H matrix, which is called as parity check matrix, to compute used in the syndrome-based syndrome vector. So how do we generate this H matrix, and what are how how is an efficient way of producing an optimized H matrix? So coming to the introduction. So let's select an error. Let me select an 7-bit adjacent error. So 7-bit adjacent error says that there are the 7 adjacent bits in an input data are corrupted. So how do we find the H matrix for that? So here is the first thing. First, we need to write down all the possible error sequences, like 1 bit, 2 bit adjacent, 3-bit adjacent, and further how many possible errors that is possible in this 7-bit adjacent errors. So once you write all the possible error sequences, then we are going to compute something called as parity bits. So parity bits are the bits which will be tagged with the input data in the memory. So which will be used for detection and correction of the input data. If there is any uh, error in this input data, by using this parity bits, we can find that where is the error and how to correct that error. These parity bits are used. So in order to generate an H matrix, first we need to find out how many parity bits are needed for this. For that, we'll use the following formula, which is shown on the screen. So the M denotes in this M denotes the received code vector bits, and K denotes the number of input data bits. So K, like in this paper we have discussed about for the 16-bit data. So the value of K is 16 in this equation, and M needs to be found by using hit and trial method. So we have used the different values, different values, and then we come to know that for 7-bit adjacent data, we need 10 parity bits. So with the help of hit and trial method, we have come with 1, 2, 3, 4, and then we came to know that value of M is equals to 10 will satisfy this equation. So we have taken that 10 is the parity bits need to find the adjacent error. So what's the flow chart we use? What's the flow we use to generate a parity, like the parity check matrix or the H matrix? So first, after writing down the error sequences, and finding out the parity bits, then we'll go for the possible syndrome vectors which can be produced by the error sequences which we previously done. So after all the syndrome vectors we produce, we generally take the column. Now we need to produce the vector columns of the H matrix. So how do we produce this columns of the H matrix? First we need to take all the vectors, and then we need to go for the vectors with the less weight. So we'll starting with the vectors which syndrome vectors which with less less ones. Then only we'll get an optimized introduction. So after that we will see that the next column which we are going to select will be the combination or the XORing of that with the other previous columns should not give any syndrome vector which is present in our possible syndromes which we have been previously. So if this case condition is satisfied, then only the that syndrome vector will be placed in our column vector. So this will be a repetitive process, iterative process. First, initially, all the syndromes with lower weights in a sense, less ones will be computed iteratively so that the H matrix will be optimized one. Then if all the vectors in the lower weight is completed, then only we'll go for the higher weight. So the flowchart which is shown on the screen will be telling you about how the columns of this is introduced. So first after the identity matrix, then the H matrix comes into play. How to add a column to the H matrix? As we see the flow, first a new syndrome is taken with the lower weight. Then the syndromes which the vector which is taken, it's XORed with the previous column. If the syndrome which is produced by XORing this two is not present in the syndrome set which we have taken previously, then only this the latest syndrome will be added to the column. Otherwise, it will be skipped and then the iterative process. Once the lower weighted ones is completed, then only will the next weighted ones will be introduced to this cell. In this way, we will produce H matrix. So in this paper, we have tried to produce H matrices for 2-bit adjacent error, as you can see on the screen, A, and 3-bit adjacent errors, 4-bit adjacent errors, 5-bit adjacent errors. These all are and 6-bit adjacent errors and 7-bit adjacent errors. These all optimized H matrix has less than once less than the ones which like the previous H matrix already existing H matrix. The number of ones in this optimized H matrix are less. So which will help us detect like reduce the area power or pat bits for this. So next part of the presentation is implementation. How this optimized H matrix in the implemented in the syndrome-based decoder with correction masking technique. So let me continue with an example. Now let us consider an 16-bit data. C is equals to this is the input data which has no error in it. First, this data is sent to the encoder and the redundant bits are calculated and are accessed to this. So first, as we have discussed, the redundant bits or the parity bits. So first it is gone through an encoder, and in this encoder, we will be finding the parity bits. So for that 16-bit data, for a 7-bit adjacent error, we need 10 parity bits. So then this encoded data along with the 10 parity bits are stored in the memory. So this as I discussed before, this parity bits, the first 10 bits of this error, this data is known as the parity bits, which will be helping for our error correction and reduction. So now let me introduce an error into this data. So now let me introduce the data in the position from 2nd to 8th position. Will be introducing like the bits are flipped. So as you can see that the last 16 bits, the from position 2 to 8, it's different from the input data, which is error free. So then now this received vector is sent through the syndrome based decoder. Then as I discussed before, if the syndrome is zero, like the bits in the syndrome is completely zero, then only we can say that there is no error. As I introduced error in this, the syndrome will be not be zero, and we'll get a by this method. Like if you see that the columns of the H matrix this is as the previous slide here, there are this is the H matrix we used for the computation. We see that the H matrix second column, third column to until eighth column are XORed, and we got the syndrome vector as here mentioned. Then this syndrome is as discussed, the every bit of this syndrome will be odd and stored in an error call in a variable called correction. And the error pattern, as this introduced, you see that the input is 3 to 1A, and 3 to 1A, the output is the first. Let me tell you about the tool we use. It's a model thing, and the language we use for this coding is very long. So as the first picture, figure number 5 tells us about the input data. The input data is 321A. The output data of the encoder, as we know that the encoder produces the parity bits. So the encoder produced the parity bits called 1 6B. This will be attached to the input data. Now this input data will be sent to the decoder. As you can see in the figure number 6, this is the decoded part of this. So the introduction, so we will be seeing that, as you can see, the first 16B321, this is the data without error. So the output will be 321A. Only the last 16 bits is appended over here. And the syndrome of this, as you can see, that it is 000, which tells us that there is no error in the input data. Then we try to introduce different kinds of errors at different positions, and different syndromes are produced, and different error patterns are produced. When the but the output, the final output which we are getting out of the decoder will remain the same because of the syndrome-based decoder which we have used, and the following H-matrix which we have used. So coming to the synthesis results from the memories. So the tool we used for this synthesis is Cadence 45 nanometer, and the language is a Verilog language. So in this paper, we are mainly focused on area, power, and delay. So for different kind of error bits, corrected error bits like 2, 3, 4, 5, and 6, 7, we have displayed the error, area, power, and delay. As we have proposed for 7 to 8 adjacent bits proposed with the proposed error, the proposed H matrices. So, as coming to the conclusion and the future scope of our paper, the implementation of optimized H matrix in this syndrome-based decoder, along with the correction matching technique, is an effective way for safeguarding the input data. So, as a result, so we can show that there is a reduction of 19%, 4%, and 27% respectively in 2, 3, 4 adjacent bit errors, and there the input data which with errors are significantly corrected, and the output of the decoder will be remaining error free. So what is the future scope of this paper? So in this paper we have some constraints, like we have taken only for the if the bits if the adjacent bits in the input data are corrupted. If there is any random bits in the corrupted data, if there is any random bits in the input data is corrupted, we can't find using this H matrices or this method. So if there is any random errors present in the data, then that will be a future scope. And one more thing, that the syndrome bits, there's a chance that the syndrome vector which we are produced, that can be also corrupted, like the data may be flipped. So protection of syndrome vector and the finding the errors in this random errors in the input data would be a future scope for research purposes. That's what I wish. So these are the reference papers which we use for our research paper. Thank you for your valuable time, and thank you for listening to me.